recording. Okay, so I think I will start because by the time I'm finished with the introduction, then everybody will have joined. So good morning, everyone. Welcome to this NEASQ webinar dedicated to some outcomes of our use case on finance, on quantum computing for finance. I'm Pascal Bernier-Bruna. I am the dissemination leader for the project NEASQ. And I have today with me Gonzalo Ferro, our speaker. Before we delve into today's subject, I would like to say a few words about our early users webinars, because this webinar is one of a series that we organize to help the quantum computing community discover and test the libraries and tools we make available. And also, we would like to get your feedback if possible. So we are organizing monthly webinars until the end of the project, so until November 2024. The full program is on our website. Also, past webinars have been recorded. So really, if you have an interest in our different use cases, visit this page about our webinar series, and you will find the links also to the recordings. So we have two webinars already scheduled for the coming months. One on the 5th of March about methods to improve the results of quantum computing measurements. This is related to our chemistry use cases. And in April, we'll have a webinar about quantum natural language processing. And registration is open, so don't hesitate to go to our website and register. So now let's go to today's subject. So our speaker is Dr. Gonzalo Ferro. He works at CESGA, and he's been involved in the NEASQ project for a long time. Also, I would like to point out that we have various resources available related to today's topic. The Financial Application Library is on the NEASQC GitHub. And also, I encourage you to have a look at the publications related to our finance use case. They are on our website on the use case webpage. So now I will hand over to Gonzalo. The floor is yours.
Okay, thank you, Pascal.
You can share. I will stop sharing, but I think you can share anyway.
Okay. So, do you see my screen?
Yes, we can see your screen.
Yes. Give me 1 second. Okay. So,
you're all set.
Yes. Okay. So nowadays in this webinar, I'm going to talk about the financial application software repository and the Quantum Quantitative Finance Library. I am Gonzalo Ferro from CESGA, as I say, Pascal. This software was developed inside the scope of the financial application users case of the work package 5 of the NEASQC project. As most of you probably know, the NEASQC project is a European project that brings together academic experts and industrial end users in order to develop new quantum-enabled applications. For the financial application use case, there is a partnership of 3 different institutions. This is the CESGA institution, is where I work. It's the Supercomputing Center that is a public foundation in Spain. We have this city that is that belongs to the University of La Coruña, that is a public university located in the north of Spain, and the city is acts as a certain type of meeting point between university and companies. And we have at the other leg the HSBC, that is a financial institution that was founded in 1865. So this is the staff of the use case. We have Andrés Gómez, that is the project manager at CESGA. We have Carlos Vázquez, that is a full professor in the University of La Coruña, that have more than 30 years of experience in the apply of mathematical financial mathematics, and this is me, this is Gonzalo Ferro, that I work as a senior researcher at CESGA. We have a PhD, that is Alberto Manzano, that works in the CITIC. And finally, from the part of the bank, we have Maria Rodriguez Nogueiras. Third, let me to talk about Organizing Supercomputing Center. Is a public foundation that is member of the Spanish Research Infrastructure and, of course, of the Spanish Supercomputing Network. And nowadays, we are very interested in quantum computer because in CESGA, we have our own quantum device that is a supercomputing device up to 32 qubits. And additionally, CESGA participates in the major quantum computing Spanish initiative that is Quantum Spain. The main mission of CESGA is contribute to the technical and the scientific knowledge by researching in high-performance application, communication, etc., and always in collaboration with other institutions. In the NEASQC project, we have developed several deliverables, several typical European project deliverables that, as Pascal said, they are available for the public in the web page of the NEASQC. We have developed 4 deliverables. There is two deliverables dedicated to the review of the state of the art of pricing and computation of VAR, and this is the 5.1 and the 5.7. And we have another deliverable that is related with the evaluation of quantum algorithms for pricing and computation of VAR. Additionally, we have released this financial application library that is the main topic of this webinar. Inside of these last 3 years, we have published several papers that we have published in scientific magazines, 4 papers, and we have another paper that is in a review process. You can see, as Pascal said, the publication in the web page of the NEASQC. So, what is the main objective of the financial application use case? Well, is researching in quantum computing for getting a solution that can use the financial industry. In general, one of the most hard problems that financial institutes have is the pricing of financial derivatives and options. So, first of all, we need to define what is a derivative. A derivative is a financial contract that depends on the future performance of one or more assets. Here, the asset is called to underlying, and asset could be any that is in the financial market. Could be stocks, or interest rate, exchange rate, credit spreads, etc., etc. There's some problem in the chat. No? Okay. Okay. Sorry.
No problem. I'm just chatting while you're talking, you know, sending URLs, that kind of thing.
Okay, sorry. We have defined what is a financial derivative, and one of the most interesting financial derivatives are options. The options are derivatives whose payoffs, the payments that the option holder receive, are nonlinear functions of the underlying. There are a lot of kind of derivative of the option, You can find the most common and the easiest one that are the European options. These options gives the right, but not the obligation to buy or to sell the asset at a given date, this is the maturity date of the option, for a fixed price, that is the strike of the option. The American options are like Europeans, but the option can be executed before maturity time. Additionally, you can find action options, barrel options, and even basket options, where the option price does not depend on a single asset. It can depend on several assets. And finally, we have these exotic options that are where the option price does not only depend on the price of the underlying and maturity. So, before to continue, we need to address the option terminology, and we have to provide the mathematical symbols that we are going to use for representing the different terms. So, one mathematical symbol that we are going to use is the value of the underlying of the option at a time t, that is represented by this uppercase S. We have the maturity, that is the date where the option expires, the contract option expires, that is represented by this uppercase T. We have the strike, that remember is the fixed price for selling or buying the asset at maturity, of course, and this is represented by this uppercase Q. We have the risk-free ratio, that is the theoretical rate of return received with a zero risk asset, that is represented by this lowercase r. This risk-free rate is not a parameter of the option, but it's a parameter of the market. And it's very important because we need it for computing the value of the option, the price of the option. That is where the price of the option at a given time t is represented by this lowercase b. That is in general a function of the time and of the value of the underlying at that time t. And finally, we have the most important term of the option, that is the payoff. That is the payment derived by the holder of the option at maturity. Well, maturity or under certain circumstances, depending on the type of the option. And this payoff usually is a non-linear function of the underlying at maturity time, and of course, of the maturity time. So, for European options or vanilla options, as we say before, the option gives the right but not the obligation to buy. In this case, we are dealing with European call options, or to sell. In this case, we are dealing with European put options, the asset at maturity for a strike price. So we can, to this box, we have the definitions, how are the functional forms of this payoff for a call option and for a put option. And as you can see here, these payoffs depending in a non-linear way of the difference between the value of the underlying at maturity and the strike price of the option. So here we have some examples of European options. These are the call options, these are the put options. Here is the maturity time of the option, and here is the strike, and of course the price of the option. So what is the major problem that financial institutions have? Of course, is to put a price to the option. This is the option price or the derivative price in general. And it's the task of finding the fair price of the target derivative contract. So in this case, when we say the fair price is a very common financial terminology. And when we say that we want the fair price, is that we want the price when the market is efficient and there is not arbitrage opportunities. So in order to do this derivative price, we need to build a mathematical model that relates the evolution of the underlying with the fair value of the option. So we want our function that relate this uppercase is with this lowercase b. So in order to do that, in the financial market, you need to understand, or you need to know the underlyings, the dynamic of the underlyings. And for this case, you need to use a stochastic differential equation. And here is where the problem arises, because for this kind of problems, the usual model that deals with this stochastic differential equation does not have, in general, analytical solution. And inside of financial institutions, there are very common the use of numerical methods. So what are the most common stochastic differential equations used in asset modeling? Well, you have this Black-Scholes model, that is the easiest one, where you suppose that the evolution of the asset follows a geometric Brownian motion. Here, this is the equation that deals with the evolution of the asset, and you need the breadth and the volatility of the stock, that usually are parameters that you can find analyzing the historic behavior of the asset. And you have this incremental Wiener process that is nothing more than a Gaussian probability distribution that have a mean and zero and a variance that is equal to the differential time step. Additionally, you can have another kind of model like the Heston model that has a sophistication over the Black-Scholes, where you, in addition to the evolution of the underlying, you can have an equation for deals with the evolution of the stochastic variance. So in this case, the Heston model is a sophistication and fits better to the dynamics of the market. We are going to work in the Black-Scholes model. In order to solve the Black-Scholes stochastic differential equation, you can find two different strategies. You can use the expectation way, where you use several stochastic differential equation methods and some financial concepts in order to arrive to that the option price will be given by this equation, that is the expectation value of the payoff at maturity time. But you need to take into account this filtration that is if t that represents the information of the market until time t. Or you can go by the partial differential equation way, but of course using again some financial concept and using some stochastic differential equation mathematics, you can arrive to this Black-Scholes partial differential equation, whose solution is this integral. So at the end of the day, as you can see, you need to compute expectation values for do pricing option, because this integral is depends, as you can see here, of the payoff of the option. In the Black-Scholes models, there exists analytical solution for particular options. In fact, for the European option, there is analytical solution for Black-Scholes models, but for other kind of options and for other models, there not exist such analytical solution. So numerical methods are mandatory. So one of the most used or spread numerical methods that in the financial institutions, is the Monte Carlo way. So we are going to deal with these expectation computations using Monte Carlo methods. So at the end of the day, we have transformed the price option problem into the computation of expectation value. We need to compute the expected value of the payoff of the underlying and maturity T when the underlying follows this conditioned probability density function. So we are going to use Monte Carlo techniques for solving this integral. So how solve integral using Monte Carlo way? Of course, you have this integral. You want to solve this integral in this domain C. In the Monte Carlo way, you have to draw this upper M independent identical distributed samples. You are going to build this Monte Carlo estimator, and by the strong law of the large number, it can be shown that when the number of draw samples tends to infinity, then the Monte Carlo estimators tend to the true value of this integral. And additionally, by the central law theorem, you can show that the error of this estimator follows a normal distribution that have a mean and zero and standard deviation that works here, as shown in this formula, with the square root of the number of samples that you have drawn. So at the end of the day, the Monte Carlo estimator have an error that scales in this way. So of course, we are going to solve this equation using this Monte Carlo estimator. And for doing that, we need to draw different underlying values and maturity time. And how you can do that? Well, in financial institutions, you can do simulation, and you are going to use this Euler-Maruyama scheme for doing the simulation. In this Euler-Maruyama scheme, you begin with the Black-Scholes stochastic differential equation. You are going to discretize the time step, and you are going to work in the say that is the risk-neutral probability measurement, that you need to change the drift of the stock by the risk-free ratio of the market. Then you arrive to this Euler-Maruyama scheme that allows you to simulate an evolution, a complete evolution of the underlying. So you are going to beginning with at a time t, you are going to simulate the underlying, you are going to arrive to the underlying value at the maturity time. And in fact, you are going to do this simulation, these trajectories of the underlying a lot of times. And the idea is you are going to gather all the simulations of the underlying value at maturity. You are going to compute the corresponding payoff because you know how is the payoff of the option, and you are going to do the average, and doing this computation from here, you can achieve what it should be, the fair price of the option at time zero. So in order to see a more graphical view of the process, we can refer to this slide. You are going to beginning with this initial time under value asset, under value of the underlying, you are going to execute a lot of computations using this Maruyama scheme, and you are going to compute the trajectories until the maturity time of the option. You are going to gather all the complete underlying values at maturity. You are going to compute the corresponding payoff. You are need to average, and then you can obtain what should be the fair price of the option at this time zero. And at the end of the day, when you do this Euler-Maruyama scheme, you are simulating what should be the probability distribution of the asset at maturity, having count the information of the market that you have until this time zero. So this is the idea. And what is the main problem of these Monte Carlo integration methods or simulations? Well, the behavior of the error, because the behavior of the error depends, as we said before, of the square root of the number of draw samples, or well, in the case of the simulation, of the number of trajectories that you simulate. And for many financial applications, this convergence is too slow. So here is where quantum computing can have an eye, because quantum computing promises that you can have an quadratic speed up over this performance when you use a quantum accelerated Monte Carlo algorithm, as you can see here. So the idea is that the error of the estimation node will scale only with the number of samples that you have drawn or with the number of trajectories that you have computed. So what is the quantum accelerated Monte Carlo algorithm? Well, here is the complete workflow of the algorithm, and here are the different steps of the algorithm. You need to load the probability density function of the asset at maturity into the quantum circuit using a unity operator P. You are going to load the payoff function into the quantum circuit using this unity operator R. You are going to combine these R and P operators into operator A, and this operator acts in the following way. When you apply this operator over the typical zero initial state of a quantum circuit, you are going to have, in the final state, you can split the final state into good states that P0 state and the bad state that are P1 state. And the main behavior of this operator is that codify into the probability of getting this P0 state the desired integral that we need to compute. So the idea is that we are going to use the quantum amplification capabilities of the corresponding Gruber operator of this operator A, and taking these capabilities and using a quantum amplitude estimation algorithm, we can have an estimation of this A that, as we said before, we have computed, we will have codified the integral that we want to desire to compute. So here, in this last step, is where the quadratic speedup is. Until this moment, you don't have any speedup. The speedup is only provided by the quantum amplitude estimation algorithm. So what the financial application software and the QQuantLib library does, of course, the financial application software allows to the user implement this quantum accelerated Monte Carlo using the evident equivalent quantum library. You can implement the different steps of the accelerated Monte Carlo, and of course, you can implement the complete workflow. Additionally, we have implemented several improvements that were developed for the quantum accelerated Monte Carlo into the NEASQC scope, were included in our library. So first, let me tell some words about the library. You can find here this library in the GitHub NEASQC repository. There are some instructions that allow you to build the complete environment. You can use the environment YAML if you prefer Conda, or you can use the requirement XT if you prefer pip to install the environment. This is where the code documentation is, and you can find a complete documentation of the library in the appendix of the deliverable 5.4 of the project. Additionally, we have created a complete interface for testing the library using Binder without necessity of download the library and without install the complete Python library. So you can test it, the library in an easy way in the Binder web page. So this is the scheme or the folder scheme of the repository, and here there are a lot of folders, but there are two main folders. This is the QQuantLib library folder, where we implemented all the code that deals with the different parts of the quantum accelerated Monte Carlo, and we have this mixed folder that contains a notebook folder. This notebook folder have a lot of Jupyter notebooks where we explain with all the details, and we provide a lot of examples of how the different parts of the library works. The QQuantLib library is split in several packages that deal with the different parts of the steps, of the different steps of the quantum accelerated Monte Carlo. For example, the two first steps, the loading of the probability and the payoff, were implemented in this QQuantLib point.dll packages. That is, DL stands for data loading. The quantum amplitude amplification routines were implemented in this AA, that is for amplitude amplification. And finally, the quantum amplitude estimation routines were created or were developed in this AE, that is for amplitude estimation packages. And finally, the QQuantLib financing allows to the user execute the complete workflow in a transparent way. So we are going to explain how this works, any of the 6 tips, and how the library, how you can use the library for executing all the steps of the quantum accelerated Monte Carlo algorithm. So, as I said before, the first thing that we have to do is loading the probability distribution. So we need to fix the number of qubits. We are going to discretize the integral domain. So remember, you need to integrate to compute some integration, and you have a domain, you need to discretize the domain into 2D values, and you are going to compute the discrete probability vector applying to the intervals the probability distribution that you want to load. Additionally, you need to create this P operator such that allows to load into the amplitude of the state the different discrete probability values. This can be done in the library with this load probability function. This load probability function is inside of this data loading module that is inside of the data loading packages. Additionally, you can see how this load probability function works using seeing this notebook, this notebook where in addition to the how this load probability function works, we provide a lot of examples of how use this function. We have implemented this P operator using the original Gruber and Rudolph algorithm in 2002, and this algorithm using an operation that is called controller rotation by state. And in general, when you use the vanilla implementation of this controller rotation by state, the quantum circuits that you are going to have are very deeper. So in the Quantum library, we have implemented quantum multiplexers that are a procedure for creating this kind of controller rotation by state that was developed by Sende et al. In 2006. Here is an example of the same unitary operator when you use the vanilla implementation and we use quantum multiplexer. As you can say, when you use quantum multiplexer, circuits are usually lower in depth, so are more suitable for NEASQC devices. Now you need to load the payoff function. So you are going to go to discretize again the domain, and you need to compute this payoff array. And you are going to load this payoff array values into the quantum circuit using this error operator. This is how this error operator works, and you see be aware, because if you are going to discretize the domain using n qubits, you are going to need an additional qubit more for creating this type of operator. Here we saw how to implement this operator, but in our library you can use you can create this operator in an easy way using this load array function. This load array function belongs to the data loading packages, as I said before, and you can see all the information regarding this function in this node, where, as I said before, we create a lot of examples for showing how to use this load array function. So now we have all the mandatory ingredients. We have this n qubits P operator that loads the probability of the decided probability density into the quantum state, and we have this error operator. We are aware because the operator, with this operator, we are going to load the square root of the payoff. This is important because it's something that we don't say before. We need to load the square root of the operator because for all works properly. With these two operators, with the P and the error operator, you are going to create this A operator that is depicted in this figure, and this E operator works as in the following equation. So if you are going to measure the last qubit, the probability of getting the zero state in the last qubit is proportional, or it's equal, sorry, to the decided Riemann sum that you want to obtain. So the idea is that you are going to codify the integral that you want to compute as a Riemann sum, and the Riemann sum will be codified into the amplitude of the probability of getting this zero state of the last qubit. So in order to implement this A operator in the Quantum library, we use this encoding class function that is inside of the data loading model. You have reference to this notebook for seeing examples and how to use. And this encoding class allows to the user implements the A operator only by providing the array with the probability discrete distribution and with the payoff function, or with the payoff array, sorry. And you need to set the encoding option to 0. And with this, you have for free this A operator. Until now, we have created an A operator that encodes the decided integral into the amplitude of fixed state. And here we have an equivalent quantum version of the classical Monte Carlo that we had before. Remember, in the classical Monte Carlo, you need to draw some samples, you need to simulate some trajectories, and at the end of the day, you are going to compute the estimation of the value that you want. And the error scales as with the square root of the number of samples. And in this case, in the case of the operator, is you execute the operator and you do several measurements, you can calculate or compute the probability of getting the zero state in the last qubit. And this probability is exactly the integral that you want to compute. And the error associated to this probability is computed or have the same functional form that the error that have the Monte Carlo. You are going to have an error that depends on the square root of the number of times you have called to this A operator. So until this moment, we don't have any speed up. The speed up comes in the following steps. When you use amplitude estimation and the amplification capabilities of the Grover operator or of this A operator. So how the Grover operator works? You have the unitary operator A, you need to execute this formula, you need to create the Grover operator using this formula from here. And the main work of this operator is amplify the probability of getting this P0 state. So in our library, this Grover operator can be built using the function Grover that is inside of this model that belongs to the amplitude amplification packages. Additionally, in this notebook, we explain how the Grover operator works and how we implemented this Grover operator inside of our QQuantLib library. Here, you can see the typical circuit from the A operator that is returned by our encoding class. And here you can see the corresponding Grover operator that is returned by this Grover function. So now we have all the mandatory steps, all the mandatory ingredients. We have the A operator, we have the corresponding Grover operator, and we need an amplitude estimation routine that allows us to estimate this probability of getting the good state, the P0 state. What are the two kind of approaches that usually are for doing amplitude estimation routines? You have two of them. You have the classical or the canonical quantum phase estimation routines, or you have amplitude estimation iterative algorithms. In the first one, in the amplitude estimation using quantum phase estimation, you are going to plug this Grover operator into the quantum phase estimation algorithm that uses quantum Fourier transform. You are doing this measurement and computing this measurement and doing these formulas, you can arrive to the estimation that you want of A. In the case of the amplitude estimation algorithm, you are going to create this circuit that apply the operator A, apply a number of fixed times the Grover operator. You are going to do some measurements. You need to post-process classically these measurements, and you are going to arrive to a new K. This new K is the number of times that you need to apply the Grover operator in the next iteration. So there is a loop where the amplitude estimation algorithm iterates again and again until the amplitude estimation algorithm returns an upper and lower bounds such that the difference between the upper and lower bounds is lower than epsilon, that usually is an input parameter of the amplitude estimation. And the idea is that the A value that you want is inside of this interval with a probability that is higher than a confidence level that usually is an input of the amplitude estimation algorithm. So in our QQuantLib library, we have implemented several amplitude estimation algorithms. We have implemented into these amplitude estimation packages. We have implemented the classical quantum phase estimation algorithm from Brassard et al. In the 2000. It was implemented in this Python class, the QQuantLib class, and you can see this in this notebook how the algorithm works and how this is implemented in our library. This is the classical one, and we have implemented again two iterative amplitude estimation algorithms. We have implemented the maximum likelihood amplitude estimation based on the Suzuki works in 2020. And we have implemented this algorithm using this MLA class, and you can find the complete algorithm explanation and, of course, how we implemented the algorithm in this notebook. And finally, we have implemented the iterative quantum amplitude estimation from Grinko that was developed in 2021. This algorithm was implemented as a Python class, as the other algorithms, in the NEASQC class. Additionally, you can see in this notebook how this algorithm works and how we implemented the algorithm. All the different classes that implement amplitude estimation algorithms always work in the same way and need the same input. You need to provide the operator, you need to provide what is the T0 state, and you need to provide the Python dictionary that allows you to configure the corresponding algorithm. Additionally, we have created this amplitude estimation class that is in this module that works as a selector. So this class allows you to select the different amplitude estimation algorithms in a transparent way. You can see this notebook in order to see how this class works. So what is the speed up? Here, in order to assess the performance of an amplitude estimation algorithm, usually you need to measure the absolute error that you have obtained versus the number of times that you have called to the A operator. And for the Monte Carlo, so for all variation of the Monte Carlo, the performance is given by this formula. From here depends as the number of times that you call to the A operator depends of the square root of the square of the error that you have obtained. For amplitude estimation algorithms, you always have a better speed up than the Monte Carlo way. The best speed up that you have achieved is the quantum phase estimation that have a quadratic speed up, and the other quantum amplitude estimation algorithms can have an speed ups or a performance that are a little better than the Monte Carlo, but can achieve or not the quadratic speed up that provides the quantum phase estimation. Here is the speed up for the iterative quantum amplitude estimation algorithm. So, until now, we have explained what part of the library deals with what part of the step of the quantum accelerated Monte Carlo, but we have developed another package that allows to the user to execute the complete algorithm. So in order to summary the complete algorithm, we have to do a little summary. So we have this asset T, we have a payoff, we have the maturity, and the objective is computing the price of the option at this time T. And the idea for doing that, you need to compute the integral of this this expectation value of the payoff of the asset at maturity when the asset follows this conditional probability function, density function, sorry. And we are going to compute this integral using the quantum accelerated method, quantum accelerated Monte Carlo method. And for doing that, we are going to fix the number of integrals. We need to discretize this integral as a Riemann sum, and we are going to lower the probability and the payoff arrays into the quantum circuit using this A operator. And using amplitude estimation algorithms, we can obtain the decided integral with different performance, depending, of course, of the amplitude estimation algorithm that we use. So, our finance packages allow to execute this quantum accelerated Monte Carlo using two different functions. With this QSolve integral function, the user can solve integrals using quantum accelerated Monte Carlo in a transparent way, but only you need to provide the arrays of the probability and the arrays of the payoff. And of course, you need to provide the configuration of the amplitude estimation algorithm. And you have another function that is the RQAE price estimation function that allows to the user to compute a complete price estimation problem using this quantum accelerated Monte Carlo in a transparent way, and the only thing that you have to provide is usual financial parameters and of course the configuration of the amplitude estimation algorithm. So under the hood, this price estimation deals with all the quantum stuff, and you need to configure the option to get the price estimation of the option. In these three notebooks, you can find a lot of information on how these integrals, these functions, were developed and how to use as an example of how to use these functions. Here we are going to show an example of how this works in real world. This is a result extracted from the deliverable 5.4. Here we have configured these different options, and of course we provide this option, this configuration of the option to this price estimation, and with this the price estimation function returns at the computed expected value for the price of the option. We need to provide the configuration of the option. Of course, we need to provide the parameters that we are going to use for model the asset evolution, and we need to provide a the discretization that we are going to use for computing the integral. So doing that, we have simulated several options. We have simulated a European option and a digital options. We have simulated call and put options. And here we can plot the absolute error that we have in the price estimation versus the number of times the operator order was called. As you can see, all the amplitude estimation algorithms works properly. There is a lot of there is a lower absolute error that we have achieved. The performance of the algorithm in general is always better than the Monte Carlo counterpart that is given by this dashed line. This dashed line. So this dashed line is the Monte Carlo simulation. So as you can see, you can obtain in an easy way and only providing these financial parameters our estimation price using the quantum accelerated Monte Carlo. So now we are going to describe some issues that the quantum accelerated Monte Carlo have. One of the main problems of the quantum accelerated Monte Carlo is that you cannot deal with positive payoffs. As you remember, this is the unitary operator, and you need to load the square root of the payoff, so you can never load negative payoffs. And this is a problem because, of course, for most of options, the payoffs are positive, but there are very interesting financial derivatives like futures that can have a payoff that can be positive or negative. And here, when you use this kind of financial derivatives, the quantum accelerated Monte Carlo will fail because you are going to but loading this negative part of the payoff. So here is an example. We have configured this financial derivative, this future. This is the configuration of the future, and we have using the price estimation function. As you can see here, no one of the amplitude estimation algorithms can properly get the option because we have lowered the bad. We have been properly lowered the negative part of the payoff, as you can see here. One of the we have proposed then into our NEASQC project a new encoding procedure that allows you to solve this issue. And the idea of this new encoding procedure is that now the error operator will need to lower the payoff array. Remember, for the all the quantum accelerated Monte Carlo operator A, you need to lower the square root, but now you are going to lower the very F. You are going to build with this R and with the P a new operator that is building using this formula. And you can show that this operator works in the following way. It will codify the desired Riemann sum into the amplitude of this 0,0 final state. And of course, the encoding class, the Q-solve integral, and the price estimation can deal with this new operator A in an easy way by only changing the encoding option from 0 to 2. So when you use the encoding option to 2 in these three functions, you can use the new A operator. And here is an example of how this new operator saves the day, because here is the before graphic that we saw in the slide before, sorry. Where we have encode the future in this A operator, and we don't have a proper estimation. And here is we have encode the same future in this new operator. And now we can see that the different amplitude estimation algorithms work properly because we have lowered currently the payoff function into the quantum circuit. Additionally, there is a second issue that the quantum accelerated Monte Carlo algorithms have. The amplitude estimation algorithms used always measure the probability of the state, so they only can estimate positive values. What's the problem with the positive values? That in fact, for several financial derivatives like futures, the final expected value that you have to compute can be either positive or negative. This is a problem because when you have a positive value, it is that you have you expect that your future provided some benefits, but if you have a negative value, you are going to have losses. So it's very important to know the sign of this value, of this expected value. So in the framework of the financial application use case, we have created this new algorithm that is called the real quantum amplitude estimation algorithm that allows to estimate instead the probability, the amplitude of the state. So using this new operator or using this new algorithm, we can achieve an correct estimation of the value that we have encoded into the amplitude, and again, we have recovered properly the sign. So this real quantum amplitude estimation algorithm can be used for this kind of derivatives that can have a final expected value that can be negative. So this real quantum amplitude estimation was developed by our collaborator Alberto Manzano with Daniel Musso and Álvaro Leitao. It was published in this paper in 2023, and was implemented into the QQuantLib library using this RQAE class that belongs to the amplitude estimation packages. Additionally, you can see how the algorithm works and how we implement it in the library in this notebook, and of course is compatible with the amplitude estimation selector class, and is compatible again with the QSolve integral and with the price estimation functions. So here we are having an example of how this works. Here we have configured a future that we know that the expected value should be negative, and of course we are going to execute the quantum accelerated Monte Carlo algorithm using the different amplitude estimation algorithms that we have implemented into the software. And as we can see here, the three amplitude estimation algorithms, original algorithms, doesn't work properly and doesn't find the correct value. But the real quantum amplitude estimation saves the day because always find the correct sign of the value that we want to compute. Additional, this real quantum amplitude estimation algorithm have a performance that is compatible with the best state of the amplitude estimation algorithms. Here, this is, of course, these are the same examples that we saw in the slide before, but we added the behavior of the real quantum amplitude estimation algorithm. As you can see, the performance of the algorithm is similar, it's a little worse, but similar to the best state of the art, that is the iterative quantum amplitude estimation algorithm. Again, we have only provided this financial application, this financial market parameter, and we have used the AI price estimation function for doing these computations. Again, we remember that in this deliverable, in this 5.4 deliverable, you can find all these experiments and all the explanations for doing this experiment with the library. So we want now to do the summary. So in the QQuantLib library allows you to implement different steps of the quantum accelerated Monte Carlo using my evident equal software. It implements several amplitude estimation algorithms, includes functions for computing integrals and option pricing in a transparent way using the quantum accelerated Monte Carlo. It provides several notebooks with how-to and examples of use. It includes a new procedure for encoding negative payoff and negative functions. This is used for negative payoffs, of course, and allows the use of this real quantum amplitude estimation algorithm that allows the estimation of negative integrals. That is very suitable for derivative pricing problems. So this is the end of the talk. So thank you for your attention. Of course, if you had any doubt, please ask it now. So I let the pass to Pascal.
Okay, so I will share my screen quickly, and yeah, and we have some questions. So they are in the chat. So I suggest you have a look at the chat, Gonzalo,
Yes.
and everyone else, because it's easier. So you can ask your question in the chat. The slides will be emailed to all attendees after the webinar. I know each time I get the questions. So, and also the webinar was recorded. I mean, it's being recorded. So, and the recording will be uploaded to our YouTube channel. So you'll be able to play it again. So we have 2 questions for the moment. Let's start with the easy one. Will all the packages used here be freely accessible for research? So yes. Yeah, that's the point. That's the point of our webinars. We share information about the open source libraries we have developed. Most of what NEASQ has developed is open source. There are a few things that are proprietary, but really there is a very large selection of open source materials. So yes, it's all available. So then there is a technical question for you, Gonzalo. Could you please comment on usage of QNNs and quantum graph NNs for stock price prediction?
And I don't know a lot of that. So in this case, I think that in the quantum neural networks, you only use a typical neural network, but use the quantum capabilities for simulating this kind of stuff. But I don't know a lot about this quantum neural networks used for stock price. And in this case, our main approach is based on the quantum accelerated Monte Carlo. And in the last part of the project, we are going to use quantum neural networks for computing bar, but not for computing stock option price. So I don't know nothing about that. Sorry. Maybe there are experts, I think that Carlo or Alberto can solve your question because they are the experts in the financial market.
Yeah, if anyone online can address the question. So, so we have an answer from the person who asked the question. Thank you very much. In fact, we're working on it. That's why I asked. So this maybe it would be interesting to get in touch.
Well, additionally, Robert said that we can use notebook for calculate interval. Sure, yes, it can. It can be. The idea is that the quantum accelerated Monte Carlo, in fact, computes integrals. You can compute very integrals. In fact, in our benchmark suite that we have a webinar in the 2 weeks ago, I think. In this webinar suite, we have used the integral computation for doing benchmarks of quantum devices. And all the algorithms that we are using, this amplitude estimation benchmark suite, were obtained from this financial application use case. So yes, you can compute in general. I suppose that you can compute typical well-behavior integrals. And we have an advantage for it.
That's the tricky one.
That's the tricky.
Thank you, Robert, for the question.
In fact, I suppose that when you have to compute integrals that are in a domain that is in high dimensional space, maybe you have a quantum advantage. The main problem maybe is with the probability loading. This is the problem because it is so that when you use this Grover and Rudolph algorithm to load the functions, maybe you don't have the expected speed up that you have. But maybe if you change or you are change the probability loading function, you can obtain a speed up, or is the idea, because the speed up always is in the amplitude estimation algorithm. So that's I think that maybe nowadays in the quantum device that we have, there is no quantum advantage. The quantum advantage is expected when the quantum computing devices improve better.
Can I add something?
Yes, please.
Sure, go ahead, Alberto.
Collaborator. So on the question on neural networks, we are working on it, but we are not sure a quantum neural network offers any advantage compared to a classical neural network. So we are doing that work and we don't have results yet, but we can keep in touch.
Yeah.
On the question on whether do we have an advantage, the answer will be if you use the same method. So if you estimate that integral using Monte Carlo, you would have an advantage.
Yeah,
But as Gonzalo was saying, for one dimension, thank you as well. But if you are on one dimension, you will never use that method for integration. You will use another one which is going to be more effective.
Yeah.
So that's the idea. If you compare the same method, yes, you have an advantage, but for one dimension, you wouldn't use that method.
At the end of the day, we need some library in order to develop the issues of the quantum accelerated Monte Carlo, because the encoding protocol, the new encoding protocol, allows to compute payoff that can be negative or function that can be negative. So we need some proof of concept library that allow us to research in this field. So could be the right person to reach. I don't know.
Can we?
For the PD, do you expectation to get the in fact, they use the Euler-Maruyama scheme. They exercise the stochastic differential equation, really, not the. You can use a partial differential equation techniques, but there is not the scope of the library. And there are other techniques that you can use for solving the probability differential equation of the black holes. Another question more?
Okay, so yeah, I see there are very interesting exchanges. So if you need to, if you want to contact anyone from the team, don't hesitate to answer the email that I will send you with the slides, and I will forward or give you the name of, I mean the email of the person you can contact. So thank you, Laurent, for the. Okay, so very good feedback to this webinar. Any more questions? So I'm glad that this very detailed and practical presentation gave rise to interesting exchanges. I think we have met people who hopefully will be able to use your research. And I hope this will lead to more exchanges. So can we close for now, or did you want to add anything, Gonzalo, or anyone from our team?
No? I said the slides before after the talk.
Okay, yeah.
I was doing some little changes
No
in the morning, so I can send
no
you the presentation before.
Okay, so thank you everyone for your attention. Thank you for your questions. I hope to see you for our next webinar on the 5th of March about methods to improve the results of quantum computing measurements. Thank you very much, Gonzalo, for this very clear presentation. I think everyone enjoyed it, and hardly anyone dropped from the webinar, and that's a really good sign. So well done, Gonzalo. And thank you, Alberto, for your contribution.
Really, the finance is Alberto. I am the program, the library.
Okay, so thank you, everyone, and talk to you soon, I hope.
Bye. Thanks.